So, as I mentioned before, in this second part, I will introduce the simulator, quantum computer simulator that we developed in our department that has been developed by our colleague Nader Kamasi. And what I will do, I will explain more or less how it works and how the output of the simulator looks like. And then we will do the exercises that we did in the previous lecture by hand. Then we will do it on the simulator. So I promise no more math. The simulator will do the math for you, so no worries, no more matrix multiplication and all these things. It will be a bit funnier, or I hope so. So before I start talking about the simulator, I would like to thanks, because I do always that at the end, that sometimes I even forget to do that. I would like to thank, so this is our team in Delft. This is the head of our group and our department, Koen Bertes, who will give you a talk tomorrow. And those are all the topics that we are working in our lab. So we have people working on the compiler and on this simulator, on the QX simulator. We have people working on the microarchitecture that is required for going, let's say, for a programming language to the signals that operate on the qubits. And we also have people working, students working on quantum error correction and fault tolerance, and also on the mapping of quantum circuits, and now on the quantum genome sequencing. So all these things explaining here, I mean, it took me a long time to understand those things. I started working on quantum 4 years ago, but it's also thanks to our students that we are capable of progressing and understanding and do something meaningful in quantum. So yeah, so say that. Let's come back to the lecture. So as I mentioned, we'll be using the simulator for the quantum computation. So why do we need a simulator? So we have quantum algorithms. So as you may know, quantum computers, we claim that they can be more powerful than any classical computer, and they will be able to solve problems that are intractable by classical computers. Like the most famous example is the factorization of very large numbers by using what is called the Shor's algorithm. And if at some point we build such a machine that is able to do that, we will crack all the security that we are using nowadays using these RSA systems. So, but the point is, like, again, we have our quantum applications, but for now, we don't have a quantum machine, right? We don't have a quantum computer. It's true that we have quantum processors that have like around 10 qubits. Like, for example, IBM, I don't know if you have heard about this IBM quantum experience. In this, we have a quantum processor with 5 superconducting qubits, 17, and I think up to around 40, 50 qubits, that it's in a cloud, and you can go to their website, and then to write a circuit, or just the way that we have expressed, the way that we have done in the previous lecture, draw a circuit and then execute it on a real quantum processor. But still, it's only like 17 qubits. But we would like to start experimenting with quantum computation without having a quantum computer, right? So that's good that we have what we call quantum computer simulator. So in Delft, we have developed a simulator that is called QX simulator, that it can run in a supercomputer, distributed memory system, and you can simulate up to 45 qubits, or in a normal desktop, in which you can simulate around 30 qubits. Because as we will see, with quantum simulators, you are limited by the number of qubits that you can simulate, and we will see why. So just a recap of what I explained in the previous lecture. So if you have a 2-qubit system, or 2 qubits, you can write down your state, in which you have to specify 4 different amplitudes, and then you have a vector that contains 4 elements. So in other words, it's 2 to the n. If now I put 3 qubits, I have a system with 8 possible amplitudes, and then my vector grows to 8 elements, right? So every time that I add a qubit, I double the size of the vector that represents the qubit. Then we have also seen that gates are represented by matrices, and in order to calculate the output state, or what happens when you apply a gate to a qubit, you have to do this vector matrix multiplication. So this is exactly what the simulator does. The simulator, what it does, it represents the qubit with vectors, and the gate, or the quantum state, using vectors, and the gate with matrices. But again, any time that you add a qubit, or in this case of like a qubit gate, the size of these matrices and these vectors grow. So if you have an simulation, so this is the number of resources that you need for simulating your quantum system. You need this memory, you need these computational resources that, for example, in order to simulate 25-qubit system, you need this amount of memories and 3.45 days to run it in a Intel processor. And for 30-qubit system, to simulate it, if you don't use any optimization, you need this amount of memory, and you will have to wait almost 10 years to get your result. Okay, that's bad. But indeed, you can play some tricks. You can do some optimizations in your simulator. So in the QX simulator, we have implemented, or Nader has implemented some of these optimizations in order to reduce the memory and the computational requirements. That, for example, to use a sparse matrix multiplication in which you only store the elements that are 1 in your matrix. You can also do dynamic state vector representation in which you don't store, you grow or shrink the size of your vector depending on the state that you have. You can also perform gate operation without doing the actual, without computing doing the vector matrix multiplication, just to swap in some elements in your vectors or in your matrices. And of course, you can always do parallel computation in a multi-core or multi-processor platform. Okay, so those are the tricks that these are the tricks that you can use in order to reduce the resources that you need for simulating quantum computation. Now, let's see how the QX simulator works. So what we do in QX simulators is we write quantum circuits, as the one that we have been using in the previous lecture. So here, you have your quantum circuit, in which you have 2 qubits, hallmark, and a CNOT, and you write this quantum circuit using a quantum assembly language, or it's also called Quasum language. So it looks like that. So you put qubits, I put the gates, and I display, I measure. I will go through that syntax afterwards. Then, once you have written your circuit, you run it on the QX simulator. But did you install the QX simulator, by the way? Yes? How many of you have installed? Okay, good. Good. If not, if you don't have a laptop or you didn't install it, you can just sit in pairs and then, share it. So you can run it, as I was saying, you run this code on the QX simulator, and this is the output that you will get. So you get a state, or you get a measurement result that I will explain this output in the next slide. So again, as I said, we use this Quasum language in order to express your circuits. So you can use this for putting a comment in, when you program, you like to put comments. Then you have to define the number of qubits in your circuit, and you do it by doing qubit 2, 3, 4, 1, whatever number of qubits are there, okay? Then you can also use this dot and whatever name you want to put them to have a sub-circuit definition. So you put, for example, dot entanglement, and then all these operations, those operations belong to that sub-circuit. That's good because then when you see the output, you can see where you are in your program. You can also define gates. That, for example, a Hadamard gate, it's expressed like 8 Q0, for example. Another thing that they didn't mention, for example, here I define 2 qubits. The name of the qubits is Q0 and Q1. If you define 3, it's Q0, Q1, Q2, and so on. You can also rename qubits. There is an option for putting whatever name you like to your qubits. Then, as I say, you can define gates. So here I do a Hadamard on Q0. I can also do CNOT, Q0, Q1, in which Q0 is the control qubit. So the first qubit in the CNOT is the control, and the second qubit is the target qubit. And here, there is a manual also in the website where you downloaded the QX simulator. There is a manual in which all these things are explained, and also it contains this table with all the gates that you can define. Pauli gates, Hadamard, any kind of rotation around any kind of axis, the phase, the T gate, the T DAC, 2-qubit gates like the CNOT, even multi-qubit gates like the Toffoli, the swap, and so on, control binary gates like the control binary gates that we use in the teleportation they are also there. So there is a set, yeah.
Let's call it normal computation, you can have only 2 gates and emulate everything else. Is it something that you can do here?
Repeat again. In
normal
normal
logics, you only need 2 operators, the not and, for instance,
the universal set of gates, you mean? Yeah. Here we define more gates than the universal set of gates, but I mentioned in my previous lecture, in quantum computing, you can also define a universal set of gates. So in principle, with Hadamard, with polygate, then Hadamard, C-node, and S-gate, you can perform any kind of computation. Okay? Another thing that I didn't mention is because there are gates that are called non-Clifford gates. That is like T-gate. It's just a classification of the gates. So when you want to go for universal computation, you are limited in the number of qubits. You are limited up to 30, 40 qubits in your simulator. But if you don't want to go to universal computation, you can go up and you use only what is called Clifford gates. You can go for 1,000 of qubits, or even hundreds of qubits. That, for example, that's the case of most of quantum error correction codes, that they only use Clifford gate for doing the error correction cycles, whatever that it means, and then you can simulate much larger number of qubits. Okay? But yeah, in principle, if I will define here only the universal set of gates, you should be able to do any kind of computation. But then you have to decompose any circuit to those gates. Okay, so, and here we just simulate, that is what happens in real devices, but here we are simulating, so we can define whatever we want, right? That's it easier. Yeah. So as I mentioned, we have binary control gates that, for example, we measure, I apply a Hadamard in Q0, I measure it out, and then the result of this measurement is, if I measure Q0, the result measurement, it's stored in the variable B0, and then I control X on B0 and another qubit, Q1. Yeah.
What's the
S gate? It's a rotation. It's just a rotation over, it's pi over 2 or pi over, S is pi over 2, Leon? S gate is a rotation pi over 2 or pi over 8.
S gate is half a Z gate. 2 times S gate is actually a Z gate.
Okay, thank you. I keep on forgetting the rotations. Yeah, thank you. Yeah? Then you also have multi-binary control gate in which I measure several qubits, and depending on the measurement result, so if the measurement result of all these qubits is 1, then I do a X gate on qubit 4, okay, or whatever qubit we want. Or we also have other control gates in which if I want any other combination, I mean that if I want to perform a big flip in another qubit based on the measurement results of the other, let's say, 2 or 3, that they should, they don't need, and I don't want to only do the big flip when it's 1. I can apply a CX gate or or I can invert the measurement result and then do the CX gate. Okay. Again, I didn't explain this very well. So usually what you do is when you big flip the third one based on the measurement result of the other, if the others are 1, you can big flip 1. But there is a possibility of inverting one of the measurement results to 1 and then invert the third qubit, let's say, if the other two are 1, 0 or 0, 1. Yeah? Now, so we can apply gates, and of course we can measure qubits. So in order to measure qubits, I do measure Q0, and I measure qubit 0, I measure qubit 1, and I can use the display. So the display here is for displaying the quantum state, the current quantum state. If I don't put display in your simulator, you will not see anything. You will say, okay, simulating, simulated, that's it. But you will not see any quantum state. So for that, you need to use the display command, or you can also use display binary only to display the output, the measurement register, so the output of your measurement. We can also have loops or iterations. That, for example, here I define a subcircuit Grover that is composed by all these gates, and I can iterate or repeat it 2 times. So I can also define that in the QX simulator. I can also put parallel sections. That, for example, here what it means is that all these operations can be performed in parallel. Okay, you can do it. You can just write them in a sequential way, or you can just write them in parallel sections. But if you write parallel sections, you have to make sure that those parallel sections are correct, and you are not, let's say, violating any dependency between instructions, because indeed there are dependency between the structures. It's not the same to do a Hadamard and a C node that a C node and a Hadamard, okay? So, but you can also write parallel sections in your code. And as I mentioned, qubits are not perfect, and gates are not perfect neither. So qubits, again, they have short coherence time, that they mean that they lose their state just because of the interaction with the environment. And on top of that, gates are not perfect neither. So if I want to apply an X gate on my qubit, and as I say, it's a rotation of 180 degrees over the x-axis, sometimes I over-rotate the qubit or I don't do the entire rotation, okay? So gates are also error-prone. So in the QX simulator, we have the option of simulating noisy circuits or qubits or circuits with errors. And for now, we have what is called the depolarizing channel or the polarizing error model that you can introduce it just putting error model, the polarizing channel, and then this is the physical error rate. And you can put the different physical error rates. And what it does, the depolarizing error model, what it consists is like an error can be, it discretizes the errors at X, Y, Z, or no error. And after each gate, you calculate the probability, or you apply these errors with a specific probability that you have defined, okay? So in principle, when you have your circuit, if you run it without errors, you should get the result that you expect. If you introduce the polarizing, if you use the depolarizing error model, you will get something different. Yeah, question. The errors. Yeah, I didn't talk about that, yeah. And that's a question that I got. So there are different ways of implementing a qubit or a quantum state, and there are different technologies. You can implement qubits based on superconducting. Of superconductors, you can implement qubits. There are silicon spin qubits that are based like normal transistors, silicon MOS transistor, which you just trap an electron there. There are these qubits that I have shown in the video, these MV centers, called MV centers. So there are different ways of let's say, implementing a qubit. Now, when I say I'm going to talk about superconducting qubits because that's the technology I'm most familiar with. So in superconducting qubits, imagine that you have your qubit, however it is built, and it has a state 0, and then I want to apply an X gate to that qubit. So in order to apply an X gate to that qubit, and the end it's a rotation, as I said, what you do is you send a microwave signal with a specific envelope, amplitude, and frequency. And when I send that signal, then I perform that rotation. And then, for example, if my qubit is in state 0, it goes from 0 to 1. But still, there are errors coming just from the, let's say, the decoherence, from the interaction with the environment. There are also crosstalk. There are other sources of noise. And on top of that, the operation, as I said, is not 100%. Yeah, it's not 100% reliable. Okay? So that's how you do perform this gate in real technology. So, as you have seen maybe in the website, we have different versions of the QX simulator. We have the command line that running in Mac, in Linux, and in Windows. Okay, it doesn't look as nicer as the other one, but this is how it looks like. And then when you run it, you get, this is the output what you get. But we also have a nicer version that is called the Quantum Studio interface, and it's a graphical interface in which here you can define your circuit. This is the output when you execute it, and you can even render the code to get the draw of the circuit. Okay. Here I will be using this one. I don't know if you managed to use this one or you are using also the command line, but you should get the same results. Now, as I said, what we do is we write a circuit using this Quasar language, we run it, and we get that output. So how this output looks like. So the first thing is that you want to get your quantum state, right? So this is a quantum state, one of these Bell states that is 1 over square over 2, 0, 0 plus 1, 1, right? I have a real part and an imaginary part because these alpha amplitudes, they can be complex numbers. And here, I only output the states that, that they have an amplitude that is not 0, right? But if I will write down the full state, I could write down something like that. But as these amplitudes are 0, I only output those two. Now, as I said, this is 1 over square over 2, 0, 0, plus 1. And to make it a bit more difficult for you guys, instead of writing down, let's say, Q0, Q1, we write Q0, Q1. So from right to left. When we were doing the math, right, we were going from left to right and writing 0, 0, but yeah, most of the simulators, they write it down in that way. So yeah, to make you a bit more confused, so we changed the order. So keep that in mind, okay? This is Q0, so let's say the least significant qubit is your Q0. That is the first one that you use, so the top qubit now in your circuit. And the least significant one is Q1 or Qn, that is the bottom qubit in your circuit. Okay, so it goes the other way around. Now, when I measure the qubit, I have this measurement prediction and this measurement register. So let's see what it is. So the measurement prediction can be 0, either 0, 1, or X. So what it does is that the simulator, it keeps track or can predict what is going to be the output of your measurement. But when a qubit is in a superposition, like in this case, you have 50% of possibilities of getting 0, 0 or 1, 1, right? That's why the measurement prediction puts, for now, an X there, okay? And the measurement register will contain the last measurement that you have performed, in this case of 0 or 1, but it's only updated after measurement. If I don't measure my quantum state of my qubit, by default, it will be in 0, 0. If I perform a measurement, I will get 0 or 1, or it will change. Okay? What else? Yeah, this is, I just mentioned that, right? The measurement contains the last measurement result, yeah, and it's only updated after the measurement. So, say this, I would like you to open your QX simulator, and then we will do together at the beginning these 3 exercises, okay? I will do it together with you, and then you can do it yourself. So let's see. I need to duplicate first the screen. I will do the first one to show you how it works, but first I need to duplicate my screen because if not, I cannot put 2 things there. Wait. This place. Okay, in the first exercise, what I just proposed is just to initialize the qubit to 0 and then apply an X gate, right? So the first thing that I need to do, can you see that or is it too small? It's okay? Kind of, yeah? So the first thing that I have to do is to define the number of qubits. In this case, is 1, right? And then an X on Q0. As I told you, the name of the qubits goes from Q0 to Qn. In this case, it's only 1 qubit, so it's Q0. And then save it. There's 1.qc. I have to put qc as an extension. And then I run it. Okay, as I told you before, as I didn't put a display, here I cannot see anything. I just say code load successfully, an iteration, and circuit execution time. So if I want to see the result of applying that thing, I have to put a display, okay? So I'm going to put, for example, a display here before I do the X and after doing the X gate. So I save, and I run. And this is the output that I get. I'm going to put it more in the center now. This is the output that I get. So first, I define 1 qubit, right? And then I just display the state. By default, in QX Simulator, qubits are initialized to 0. So if you don't do anything, they are initialized to 0. If you want to make sure that they are initialized to 0, you can also use a command that is called preset. And if you put preset, it's the same. And then, so here is my 0 state. Then I do a bit flip on the X gate, and then I go a bit flip, sorry, on my qubit, and then I go to the 1 state, right? And because I'm in the 1 state, my measurement prediction says that if I measure it out, I will get 1, but my measurement register is still in 0 because I didn't measure it out. Okay, so the measurement register it's updated once you perform a measurement. It's not, it's 0 by default. Yeah, if I now, for example, if I put now and then I display again, that should be updated. Oh, measurement here. It's mess, sorry. Measure, it's measure, right? Not measurement. Here, now. If I measure now the qubit, as I said, after measuring the qubit, the measurement prediction is still 1, but then my measurement register changes to 1, 2. Yeah?
Inside the parentheses, is that a complex number, real part and imaginary part?
Yeah. Yeah, because these alphas and betas, that's something that I think I didn't mention, that they can be complex numbers. So that's why we put both parts. But here they only have the real part. Okay? Okay, so that's a very simple example. So here, if I run it several times, because it's in state 1, I will always get 1 as a measurement result, right? So I can iterate, so you see it's changing, so I'm executing, see that number there, but it's always 1. Yeah? Now let's try to do the second one, in which I have a qubit in state 0, and then I do a Hadamard, and then I measure. Let's see what happens there. So now, I declare again, I define 1 qubit, I'm going to display the state, then I do a Hadamard, and then I'm going to display again. For now, I'm going to measure, I just want to do that, okay? So I save it. You can also, as I told you, you can render the circuit, and I should get. So you can also have your circuit there. Okay, so again, I save it, and I run it. So here again, my initial state is in state 0, because it's initialized to 0 by default. Then I do a Hadamard, so I have 1 over square over 2, 0 plus 1. And then, because it's in a superposition state, as I mentioned, the measurement prediction, it says X, because you don't know what you are going to get as a result, right? And for now, the measurement register is initialized, it's 0 by default, okay? Now, if I measure Q0, and I'm going to display after measurement, then here, after doing the measurement, after doing the measurement, it happens two things. First, my state is collapsed to 1, okay? So it goes to superposition to 1, and on top of that, my measurement register says is 1, and my measurement prediction also says 1. What will happen now if I run, yeah?
That's my question.
What will happen now if I run that several times? Yeah, so let's run this circuit several times. Let's see what happens. So now it's 0. Look at the last two lines, 0. Now it's 0 again. Now it's 1. Now it's still 1. Now it goes to 0. So 50% of the times, if I do, I run this circuit using this loop, so iteration several times, and I do the average, around 50% of the times, I will get 0, and 50% I will get 1.
Distribution. Do I do like a cycle, like a for, or do I do in parallel different copies of the system to extract the probability function of getting 0 or getting 1? Did you understand my question?
So you're going to get, the question is that you're going to get the probability distribution of getting
Yes.
0 or getting 1.
What is the best way to do it with a quantum computer? I do several copies of the same system, right? I have qubit 0, 1, 2, 3, 4, 5. I do the same Adamar to all of them and then measure in the end, or do I get one
But when
qubit?
you say the probability distribution, you're going to get the values then on alpha 0 and alpha 1.
Something like that.
Okay, so that's possible. It's what I say. When you measure your single, when you have, I'm going to talk about a single qubit state, okay? It's easier to understand. So you have a single qubit state, and you prepare, let's say, in whatever superposition state, so you apply a Hadamard. And then it's perfect Hadamard, and it's 1 over square root 2, 0 plus 1. But you don't know, you don't know, let's say, the alphas and the alpha 0 and the alpha and beta. So if you measure it once, you will only get or 0 or 1, right? So you cannot know the alpha and the beta. But if you prepare the same qubit several times in the same initial state, whatever superposition it is, and you measure it out 1,000 times, then you can get the values of alpha and beta. That's the way to do it. You cannot get the alpha and beta with a single measurement, but you can get the values if you prepare your state always in the same state, and you measure it out several times. That's how you can get the alphas and betas.
My question is, in this case, you only worked with 1 qubit. So I could work with 1,000 qubits in parallel and extract from that the probability distribution. And if my answer to my calculations is in the probability distribution, is it better to do that way, or is it better to do it like a cycle? I start with 1 qubit, do the calculations, repeat, do the calculations, repeat. So
no, you can do it with all the. You can prepare them. Let me think. On the same extent, you can prepare the extent that you want. Then you measure it out, and if you measure several times, you will get, for example, the state 0, 0, 0, 0, 0, 1, 10% of the times, or the state 0, 0, 0, 0, 1, 0. You see? That's the same way that what a single qubit gate. You also do it like that.
okay,
So.
thank you.
Okay, so then I leave it to you. So, oops. Let's do now exercise 3, in which I start with a 0 state, and then I do Hadamard set Hadamard, and I measure it out.
Just one question. Initially, when it starts, the state of the bit is always 0?
Yeah.
0, okay.
It's by default it's 0. If you want to initialize it to 1, you have to do an X gate. Okay? So let's do exercise 3, in which, again, I declare 1 qubit, qubits 1, and then I do Hadamard set Hadamard, and I measure it out. I'm going just to walk around to see if you have any question. So we have seen in the previous lecture that if I apply, where is it, a set Hadamard, It's equivalent to applying what gate? Do you remember? An X gate? Yeah? Okay, so you write down that in your simulator. You should get something like that. Again, here I displayed the state. So the qubit is initialized to 0, and then I apply all these 3 gates. I'll display, so it's in the one state, and when I measure, of course, I get the one state. Okay? Let's do something now with 2 qubits. Now I have a 2-qubit system, so you have to put qubits 2. You have to declare 2 qubits. Again, the top qubit is the Q0, and the bottom one is the Q1. And I have to apply an X on the first qubit, so, and then a 0 between qubit 0 and qubit 1. Okay? And this is the exercise that we did also before, so you should get the same result that you got before. Let's use this one that it's easier to see. So this is the circuit that you have to write, right? And you can change, I mean, you can assume that Alice wants to send a 0, or she wants to send a 1, or you can do any kind of rotation using this rotation case, so you can do rotation in any of the axes, and then see that actually, using this binary control gates, Bob receives the state that Alice wants to teleport or to send. Okay? So in this case, you have to define 3 qubits. Again, the top qubit is the Q0, and the bottom one is the Q2, and that means that in the output state, the state that Bob will receive is the most significant bit, and the state that Alice wants to send is the least significant bit, qubit. Yeah? I will walk around, and if you have any question, I will show the circuit afterwards. Yeah?
So those rotation commands will be useful if we want to give Alice random information, right?
Exactly.
That we use here.
Yeah.
Yeah, okay.
I would like you first to use a 0 and a 1, and then you put whatever state there, just using a rotation, an arbitrary rotation. Okay?
Just have a question regarding the teleport.
Okay, so I hope that you managed to write down the circuit of teleportation and it's working. If not, let me know and I can have a look at it. So, yeah, with that, I would like to finalize my lecture today. So I hope that you learn at least a bit about quantum computing, and that you know at least to explain what it's about, and just to, yeah, do simple circuits. So there are a lot of things that I didn't explain, as I say, like quantum error correction or like how to build a quantum computer, but those are things that Koen will explain tomorrow in his lectures. So I hope that you enjoy it. At least I enjoy it. That's good enough or not. So, and yeah, and please feel free to ask any question.
Okay, let's thank the speaker. Okay, so now we have some time for questions. I don't know who's for questions. One there. Okay, so let's use mine.
Okay. So what explained here is, I think it's really the fabrics of what might be a computer. So I saw in your team, you have people dedicated to architecture and compilers. So how far are you in a real CPU architecture using these as, I think, as the basic gates as we are used to chip design? And how far are you also in the compiler space? Because I know that you have people on your team working on it. Can you just give us a little brief of?
Yeah. Okay, now I'm going to spoil Koen's talk for a bit. No, sorry. No, so in our team, so as I say, so Koen is the head of our lab and our team. So as you say, we have different, we are working on different aspects of the computer architecture, because we are I'm not a computer engineer, but they are computer engineers. I'm an electronic engineer. So we are working on a higher level programming language that is called, and compiler that is called OpenQL. In OpenQL, you can write programs in Python or C++, so we support both languages. And then you can compile it, so writing down, you can compile it to the what we call quasum. Now it's called C-quasum. It stands for common quasum. And with this C-quasum, you can simulate it on the QX simulator. That is a bit different than the quasum that we were using today. But you can go one step further and compile it to what we call E-quasum. E-quasum stands for executable quasum. That those are the instructions that go to your microarchitecture, because we have built a microarchitecture for controlling a superconducting processor. And then in the microarchitecture, those instructions are translated into the pulses that go into your quantum chip and operate on the qubit. So as I mentioned, we are also working, we are working on compilers, we are working on programming languages, on microarchitecture for the real experiments, and we are also working on quantum error correction. So as I said, qubits are very fragile units and they need to be protected against errors. So the basic idea of quantum error correction is you work with logical qubits. Logical qubits are composed of several unreliable physical qubits. And on top of that, you have extra qubits in order to check the status of your system, to check if there was an error, what error happened, and we are also working on the decoding process. So for example, what an error happened, how to identify that error, so in which qubit and what error occurred. And we are not really working, the only thing that we are not working that much is in applications of quantum algorithms, but it's true that Kuhn started a new line of research in quantum genome sequencing, because we like to investigate how quantum can be good for specific applications. And I think I'm not missing anything. Another important thing also is that we have, let's say, all these things, we have like two lines of research or two parallel things. So we look at the real experiments. So what is required for controlling the superconducting qubits as well as the spin qubits. Those are the two technologies that for now we are focusing on. But we also look at the scalability. What if we have 1,000 qubits? And for that, we run simulations. So for example, one of our PhD student that is here, Leon, he developed a platform for simulating the microarchitecture and then to investigate, to do a design space exploration and to investigate how the microarchitecture will look like if we will have thousands of qubits. Because you cannot wait till the qubits are there for start thinking about all these things, right? And the same for the compiler. And so that's. But as I told you, Kuhn will explain all these things tomorrow, and you will see you have the big picture. Okay? This is just introduction, just the basis of quantum, but nothing to do with building a quantum computer.
So I have another question here.
Yeah.
Hi. So what's most of the examples that we have seen are, at least I can imagine them as being reproducible in classical computing. They're very simple as we can, so that we can understand them. But what's the differential hello world of quantum programming? So what's the simplest program that illustrates the specific advantages of quantum computing?
Okay, good. Okay, first of all, so it's just as I mentioned before, so the main difference is this superposition and entanglement that you don't have in classical computing. What we claim is that quantum computers can be faster than classical computers, just exploiting those phenomena, because you have this maximum parallelism in your computation, right? Have we shown theoretically? There are people who prove that quantum computers can be much faster than classical computers, but there is no real proof. Nobody shown so far that a quantum computer or quantum processor can be faster than a classical computer. So theoretically it's there, but from an experimental point of view, there is no demonstration of exponential speed up. So examples, there are several examples from an algorithm point of view. Okay, that for example, the most famous example is this about factorization. It's not the most realistic one, because for factorize, for example, a 2,000-bit number, you need like millions or even billions of qubits, in principle, for doing that. But if you want, for example, to decompose a 2,000-bit number with a classical computer, that's kind of impossible. But with a quantum computer, a big enough quantum computer, you could do it in a bit more than 1 day. So that's the thing. An example of that is what I told you. Example of that exponential speed up right now, there is none. There are just theoretical work on that, but not a real proof. That's.
Sure.
But I think that Grover algorithm is simpler than factorization.
Grover's,
right?
yeah, there's also this Grover's algorithm.
So do you consider that this already has this difference in theoretical complexity? Would it be the simplest one, or is there a simpler, like the one that you would show if you want to convince someone that is not convinced with quantum computing, so like saying, oh, I could do this with probabilities, okay? For example, entanglement, it really sounds like a 0.5 probability. I could do this with instead of 0 ones, an interval between 0 and 1. So would Grover be the simplest example that would show that this is not enough, or is there any? I'm asking because I really don't know.
Yeah, no, sure. So, no, I'm not an expert on quantum applications or algorithm, but Grover's it could be a good example. I mean, in which you can search, it's for searching, right? I mean, you can search on all these states at the same time. So you get the answer, let's say, in one shot, and you don't have to look at all the states to get your answer. Because, for example, yeah, this for searching, you have an ordered list of whatever data you want to look in classical, you will go one after, you will look at the first element, then at the second one, and the third one, and so on, right? To find the element that you want to find. And then if it turns out that the element that you want to find is the last one, you will have to go through the entire list to get your state or the element or whatever you are looking for. In quantum, you can look at all these elements at the same time and get your result in one shot. That's a good example indeed. Thanks.
Perhaps I have one suggestion, that the simplest hello world that you can have is hello world and not.
Okay.
Okay, so we have time for another question?
There's one question.
Well, this is more technical question. I understand that the simulator allows to take into account noise and decoherence, but what is the maximum number of qubits which are spoiled coherently? I mean, usually you are much less protected against correlated errors than against random errors at separate qubits. So what is the main error, the biggest error you can simulate in your system?
You mean in your simulator?
Yes, in the simulator,
okay.
Yes.
Okay, so I just mentioned that, for example, the one that I've shown in this simulator, this depolarizing error model, is not very realistic because it assumes that this depolarizing channel, in which you have uncorrelated errors, but errors are more complex than that. Now, there are our colleagues in TUDEL, so Leo Di Carlo, who is working on superconducting qubits, they are developing more realistic error models in which they take into account not only the errors coming from the gates or from the qubits, but also the correlation between them with you have other sources of noise or errors in your system. What those errors are, to be honest, I don't know. We have to ask him, but they are working on those error models. And they will be included. So for now, so they are working on those error models, and our goal is to include these more realistic error models in other simulator. Okay, so this is the basic thing that you can play with, but indeed it's not realistic. So, but it will be available soon. I will send an email around.
So you said you were working with superconducting qubits, right? And you mentioned that you would use microwave pulses to change the qubit orientation, for example, a NOT gate. Mm-hmm. So how would you implement a Hadamard gate in that circumstance? Because you need to take into account a quantum state that you do not want to collapse. Not a Hadamard, but well, actually, yes. So how do you spin one qubit, taking into account the state of another qubit, using microwave radiation, and without collapsing another one?
Okay, so I don't know if I understood your question, but what it does, I mean, is the gate At the end, in superconducting qubits, they are microwave pulses.
CNOT gates, that was my original idea. Sorry. Yeah.
A CNOT gate is more complicated than that. In a CNOT gate, so it's interaction between two qubits, and for that you have to do have a kind of decoupling or coupling between them, in which you have to change the frequencies, put them together, and on top of that use a microwave. I don't know the nitty-gritty details, because I don't remember now exactly. I can show you a paper in which they explain that. And on top of that, a CNOT gate, in this technology, you cannot implement a CNOT gate, at least for the transmons, so the technology that we are working on, but a CNOT gate is implemented by a C phase, that is a control set, and 2 Hadamars. So it's 2 Hadamars, but plus a C phase. Okay? And yeah, how they are implemented is more complicated than just one signal. It's about playing with the frequencies of the qubit and put them together and then to separate them.
Okay, any more questions? Okay. Oh, sure.
Sorry, thanks. You mentioned that about a universal computer, that we are limited in the number of qubits in a universal computer. Why is that?
It's because of this thing that I explained. It's because of the kind of matrices that you get when you use universal gates. So when I use non-Clifford gates, I get, like, say, more complex matrices with less zero elements, and then you have to store all of them, and then you cannot optimize that match. If you use only Clifford gates, let's say you have a pattern or more regular matrices in which you can really optimize, and you can play with that and go for higher number of qubits. It's because the information that you have to store.
So it's a technical limitation. It's not a theoretical.
It's technical limitation. That's technical limitation of the things that you have to store, and how the matrices look like, and the elements that you have to store and play with.
Okay. One last question.
Okay.
So I remember that you draw the sphere when representing the qubit, and you are making approximation to the binary code 0 and 1. So in my idea, you are splitting the sphere in two and checking if it's 0 or 1 and pushing that limits. Couldn't we just, instead of just splitting the sphere in two, could we split it in 4, and instead of using digital binary code, use a different kind of code, like a 4-state code? So my first question, is it possible only to measure 0 and 1, or can we measure 0 and 1 and the radius, for example? Because in your example, you are approximating to measure 0 and 1, right? One vector. But the vector can have a radius. So we can measure 0, 1, AB, for example, like on the poles. Is it possible to do it?
But then you are on the poles, you are in a different state, right? So I don't know if I understand your question. So yeah.
So the sphere, right? So
yeah,
and then you show the vector, and we are pushing the vector up 0 or 1 and pushing down to the other value. But we can push also the vector down and left, and then we can go to the right side of the sphere.
Yeah, but then you are in a different state. So what it represents is the state of your qubit, right? So if you are in 0 are here and you are in 1 are there, let's say. And if you are in whatever superposition state, you are somewhere around, right, in your block sphere.
So instead of make an approximation to a one binary state, could we have 4 states instead of binary? Can we measure that from the qubit?
I don't know if I understand the question.
Yeah.
But I think what you were assuming is that we were taking the sphere and considering that one hemisphere corresponds to 0 and the other hemisphere corresponds to 1. And I don't think that's what happens. You have the poles, and each state around the sphere represents a probability of either getting 0 or getting 1. They're all possible states, and they all are used for computations in principle. Okay? But for this case, we are using a sphere to represent a qubit, right? So that's intrinsically binary. Okay? So
but it's like a continuous variable. So
yeah.
Cardinal states, I'm sorry, you have different cardinal states that you can measure indeed. So you can indeed, in principle, measure any point on your block sphere. But you want to limit it to, let's say, the universal set of gates that you're using. Yeah, and those states that they put the qubit in, those you can always measure. And this is the universe in which the qubit is actually moving. You can always deviate from these things. That's one of the challenges that we have. So yes, there are more. I think there are 8 cardinal states. Yeah, that you can
You mean that you collapse in a different, maybe it's related to the measurement because you can, is that, yes?
So you have different cardinal points where you could also measure, just instead of measuring two states.
Yeah. So you can measure in different bases. So for example, here in the examples, I was measuring in the computational basis, that is 0, 1, but I can measure in other bases like the plus and minus 1.
That's for on my head.
That's,
here we are making
Okay.
like an obsolete layer on top of the quantum computing. It's the 0 and 1, but this can leverage a lot if we just don't think on binary and think on ternary code or quaternary code or octa-code. Right?
yeah, okay. You wanted to say something, Leon, to add something to that?
Yeah, it was actually related to the question. The only thing I wanted to say that I had the feeling that you were also targeting the question about having multiple, like you said, instead of only 1 and 0, having multiple entities in them. And yes, that do exist, so-called multi-level systems. Like in binary, we also have like multiple level patterns. In qubits, also multi-level systems do exist, but they are inconvenient to use, just like we use binary logic instead of more complex. Oh, sorry, thank you very much. Just like in computers, we also use binary logic just because it's easier to implement. So, but multi-level systems do exist.
Yeah, we only use the first 2 levels of energy. That's, so, yeah.
Okay, anyone with a question? So before you go, I have to say, and before we thank Carmina for her wonderful 2 talks, I know, don't go away afterwards because Louise has something to tell you about the hackathon. So stay put. Now, if there is no more questions, let's thank again for this wonderful, wonderful lectures.